All right. Good day. I'm recording this because the class recording didn't work. So this will serve mainly as a refresher for those who were in class and those who didn't come to class who feel they have better things to do. Well, I hope this helps you one way or the other. I'm hoping this is not going to be more than 5 to 10 minutes because I'm just going to go through it real quickly. So just before Thanksgiving, we stopped right here. We started looking at hypothesis testing, and this was where we stopped. We looked at three techniques. We looked at the confidence interval approach, we looked at the z-test approach, and then we looked at p-value. Today, we're going to look at the t-test approach, which is very similar to the z-test approach. And then we'll look at the t-test function, which more or less just brings everything together. So this piece here is simply a conclusion for whatever we were doing the last time. And this is another test that we are supposed to run. Test if the population mean age is 31, confidence level is 99%, use p-value approach. You set up your hypothesis. I was emphasizing this in class that it's important for you to understand and know how to set up your hypothesis properly. If you can get that done properly, more than half of the work is done. All right, so we're using this file BDIMS CSV. It's in the LMS. You can always download it from there. To calculate our z-stat, we need the x bar, which is the mean of the age, the s, which is standard deviation, number of rows. Our confidence level is 0.99 because we were told that confidence level is 99%. That also means that our alpha is 1 minus 0.99, so 0.1, 0.01, sorry. And mu is 31. That's the claim. We're told to test that the age is 31. So that's our claim. So let's run this. Alpha. And calculating our z-stat, we've seen this formula severally. X bar minus mu divided by s over square root of n will give us our z-stat. And our p-value is p-num of z-stat. Okay. Now, something is here. It says z-stat is negative, focus on left tail. Okay. What that means, when you are using the p-num function, p-num, so the first parameter is your value, in this case, our z-stat, then mean, which is going to be 0 for us, because then standard deviation, which is 1, then lower tail is true. That's the left tail. The lower tail is the left tail. Now, because our z-stat is negative, we want to focus on our lower tail, which is what is written here as left tail anyway. We want to focus on our lower tail, and so we could say lower tail equals to true, or we can skip it. It's the default. Okay. If our z-stat was positive, then we want to focus on our right tail or the upper tail, and in that case, we'll have had to say lower tail equals to false. Okay, but since lower tail is since z-stat is negative, we'll keep our lower tail to be true, and then we'll compare the two values. Naturally, if our p-value is larger than our alpha divided by 2 in this case, then we fail to reject. If p-value is less, then we reject. In this case, our p-value is greater than alpha divided by 2, so we fail to reject the null hypothesis, and we say that we are 99% confident that population mean age can be 31. Let me state this at this point. C-level officials, VPs, directors, and such people, they are paid so much for their decision-making prowess, for their risk taking and stuff like that. As a business analyst, you will be paid for your conclusions. That's what you're being paid for. In reality, I can get a high school kid to run a lot of this functions, do a lot of these calculations, but the conclusions that you make at the end of all this exercise is how you justify, your income. Why am I saying that? It is important when you do any work like this, any analysis, whether you're doing it in class for homework or exam, or you're doing it on a project outside of school for work or anything like that, to write a meaningful conclusion. I always say let your conclusion include 3 things. One, what the conclusion is. Are you rejecting? Are you failing to reject? Why? Okay. And at what level? The reason why the level is important is because at a different confidence level, the conclusion might be different. So please bear that in mind. This is another similar example. I'm not going to go into that. You can work on that. I want to skip to the t-test approach, which that will be the 4th technique. Okay, the t-test approach. So we've been looking at this normal distribution, and we'll be using the z-tests all along. But when you don't have a large data set, primarily when your data set is less than 30 rows, you should use the t-test because it's optimized for smaller data set. When you look at the normal distribution and you compare it to the t-distribution, they are not necessarily different, except that the normal distribution has a higher peak in the middle, while the t-distribution is flatter. That's just because there are fewer data sets. The data set is smaller. And you can look at an image in this URL. It gives you an overlay of the normal distribution on top of the t-distribution if you want the visual difference. Everything I just said a couple of seconds ago is what's here. So let's keep reading. Oh yeah. When the sample size is large, z-test and t-test result in the same values and conclusions. It means that the t-test can be used in any occasion, whether the sample is small or large. But if the sample is small, you do the z-test. This is a procedure to follow. The first thing you need to calculate is your t-stat. This is similar to what you do when you calculate the z-stat. X bar, which is the sample average, minus mu, which is the claim, divided by S, which is the sample standard deviation, divided by the square root of n. N is the number of rows you have. Then you also calculate your t-crit. Remember, for z test, we calculate the z-crit. In this case, we are calculating the t-crit. We're using the qt. We're using the function qt, not qnum. The qt takes a second parameter. Qnum takes only one. The q take more than one, but we're only feeding it with just one parameter, but Qt takes the second parameter, which is the degree of freedom, and it's important. The degree of freedom is the number of rows in your data set minus 1. So the T-crit is like this, the absolute value of Qt of alpha over 2, and then you pass degree of freedom, df, as well. Then you compare both of them, and you come to a conclusion. If your T-stat falls between your negative and positive T-crits, then you fail to reject. If your T-stat falls outside of your negative or positive T-crits, then you reject the null hypothesis. So let's look at a concrete example. A sleeping test is taken from the population. 7 hours is the claim. The result of the sample is below. We want to test at 90% confidence level. Again, in class, I try to slow down and explain each of the sentences or what's exactly is going on here. But this is just a review, so I'm going to move on. N is 20, X bar is 6.5, S is 0.7, alpha is 0.9 because it is 1 minus 0.9. Mu is 7, that's our claim. Degree of freedom is n minus 1, which is 19. Let's execute all of that. T-stat, the formula is there, X bar minus mu, S over square root of n. T-crit is there. And then we do our comparison. So our T-crit is 1.73 or 1.729133. So negative of that all the way to positive of that. And our T-stat, on the other hand, is negative 3.194383, which is outside of our range. So in another way, you can say it's within our rejection area. And so in that case, we get to reject our null hypothesis. All right, so we say we support the idea that mean sleep hours in the population cannot be 7 hours at the confidence level of 90%, right? Now, let's round it up by looking at the t-test function. The t-test function takes everything that we've been looking at and kind of tries to make it a lot easier. So with the t-test function, you don't have to calculate your t-stat or t-crit or any of that. You just run the function, it spews out a report. You read off your report. In your report, you have the p-value. In your report, you have the confidence interval. And based on those two, you can come to a conclusion, write your conclusion, move on to the next problem. Very simple, very straightforward. All right. The t-test function call, the t-test function call looks like this. The first parameter or the first input is your data set. Most likely your vector of age or vector of mileage or vector of whatever it is that is your sample. The next parameter is your alternative. This refers to your alternative hypothesis. So if your alternative hypothesis is not equal to, then it's a two-sided test. If your alternative hypothesis is mu, now we're talking of the alternative, not the null hypothesis. If your alternative hypothesis is something like mu less than, then it's an L, or it's a less than hypothesis. So you use less than or you use L. If your alternative hypothesis is greater than, mu is greater than something, then it's a greater than hypothesis. You can use G, you can use the full word greater than, the full phrase greater than. It recognizes the first letter. So whether you say the letter T or the letter L or the letter G, it understands what you're trying to say. Then you have mu, which is the claim, and then our confidence level. Let's look at a concrete example, which will give us a report, and we can read off of that. One important thing here, so far with our t-test, z-test, we divide our, we divide our alpha by 2. In this case, we don't need to divide our alpha by 2 because the p-value in the report is for the total of 2 sides. So just something to bear in mind. Test the claim that the mean height of people is 171 centimeter at confidence level 90% from the same data set. So let's construct that. This is our hypothesis. Null hypothesis says mu is equal to 171, and our alternative hypothesis says mu is not equal to 171. Because it's not equal to, that means we are doing a two-sided alternative hypothesis. All right, let's continue. Then our function call, t-test, that's a function, right? B height, $height is our data set. Alternative is two-sided because it's not equal, right? Our mu is what we're given as the claim, which is 171. Confidence level is 0.9. And if we run this, we will see what the report looks like. The report is right here. Degree of freedom. So this is actually a data set with about 507 rows in it. This is our p-value. This is what we are looking for. Our p-value is 0.7309. Our p-value is larger than our alpha. Our alpha is 1 minus 0.9, which is 0.01. So in this case, because our p-value is larger than our alpha, we fail to reject the null hypothesis. But before we go further, let's take a look. Our mu is 171. If you look at the confidence interval that we're given right here, 171 falls within that range as well, right? 171 is greater than 170.4553, and it's less than 171.8322. So your conclusion can be off of the p-value, or it can be off of the confidence interval, or it can be off of both. But the t-test function, gives us enough reports to be able to basically make our conclusion. But don't forget, when you write your conclusion, state your confidence level. State your confidence level so that someone doesn't redo your work at a different confidence level and come to a different conclusion and then challenges your work. I'm going to stop there. All of this are the same thing, using the t-test function, using different data sets or different columns, different mu values, different confidence levels. And there are a number of such exercises here. The good thing is the more you practice, the more comfortable, the more confident you are at tackling this kind of problems, right? I'm going to stop here. If you have any questions, you have my email address. Please feel free to reach out.